All right, jumping into 10.2, I'm going to do this one in Word as well, just because it's a little bit easier to type it out than it is to write it all out. So the last section, section 1, was a very big section. We were looking at sequences, infinite sequences, and we saw a bunch of different theorems and concepts and definitions for that. Now we're jumping into infinite series. So the difference between a series and a sequence is that a series, you are adding up an infinite number of terms. Instead of just looking at a list of an infinite number of terms, which is a sequence, series is that you're actually adding them all together, and it's that infinite sum that we're trying to find. So just to kind of start this off, we're going to start this off with an example. 1 plus 1/2 plus 1/4 plus 1/8 plus forever and ever and ever. So every single time we're dividing by another 1/2 to get to the next term. Okay. So what I'm going to do here is I'm going to make a table. I don't know exactly how big I want this table to be. Let's just start off here. Okay. Wrong thing. There we go. So what I want to do with this table is we want to start by finding the sum of a finite number of terms. And then hopefully that's going to lead us to get to the sum of the infinite number of terms. So this first column is going to be my n value, which is the number of terms that I'm going to be looking at. The second number here is going to be the value of that particular index. The next one is going to be the sum of those three terms. And then this fourth column will come to in a little bit. So let's just start off with my index value of 1. The value of the series at 1 is going to be the 1 that's out in front here, which that's the only value that I have. Then, of course, the sum is going to be 1. Okay. The next index 2. So the next index 2, the value at the index 2 is going to be 1/2, which means that the sum at index 2 is the 1 plus the 1/2, so 3/2. Okay. At index 3, the value at index 3 is 1/4. The sum at index 3 is 1 plus 1/2 plus 1/4, which is 7/4. And then I'm going to skip a little bit. Let's go to index little n, if it'll stay little n. Okay, great. So the value at index n, we have to be a little bit clever with, it's going to be 1 over 2 to the n minus 1. So you can kind of see that just from these values up top here. If I plug 3 into this, I have 1 over 2 squared, which is going to be the 1/4. So this is just representing the nth term of my series. The sum at that part, so here we got to get a little bit clever. And to figure out what the sum is at the nth term, we're going to look at these previous sums. It started off with 1, and then it went to 3/2, and then 7/4. And if you keep doing this, you'll start seeing a pattern. I would never really expect you guys to get this pattern right away. It's kind of a hard thing to get, but maybe once I write it out, you'll see that this really is the pattern. It's 2 to the n minus 1 up top, divided by 2 to the n minus 1 power on the bottom. So this n minus 1 is the exponent here. This is just 2 to the n and then a minus 1 in the numerator. If we plug 2 into this, I'm going to have 2 squared, which is 4 minus 1. That's where this 3 is coming from. If I plug the 2 into the denominator, that's going to be 2 to the 1 power, which is where this 2 is coming from. If I plug 3 into this, 2 cubed is 8 minus 1. It gives us the 7. Plugging the 3 into the denominator, 3 minus 1 is 2. 2 squared gives us the 4. So this really is the pattern for the sums of just the first n terms. Okay. The next thing that we want to do is that this is the sum of the first n terms. If I take this sum as a sequence and take that sequence as n goes to infinity, that's going to give me the sum of the infinite series. Okay, so I'm going to say that one more time. If this represents the sum of the first n terms, if I take n going to infinity, it'll give me the sum of the infinite number of terms. The problem here is if I take n to go to infinity, I'm going to get infinity on the top and infinity on the bottom. We could either try to do L'Hopital's rule, but that's not really going to help us here, Or what we can do is we could rewrite this. To rewrite this, we're just going to divide the top and the bottom by that 2 to the n minus 1. So what we end up is 2 minus 1 over 2 to the n minus 1. Like that. Oops, sorry. So this was just taking 2 to the n minus 1 and dividing it by each of those terms up top. Now if I take n to go to infinity, this term just goes to 0, and then I just get the value 2. I.e., in other words, that infinite sum that we have up top there, 1 plus 1/2 plus 1/4 plus 1/8 plus forever and ever and ever and ever, that infinite sum is 2. Okay, so I hope just you kind of take a minute, pause the video if you need to, and really think about how crazy that is. How crazy is it that we are adding up an infinite number of values, and that infinite number of values comes out to be a finite number? All right, good. So let's move on to some definitions. So our first definition here, given a sequence of numbers, that sequence of numbers being this, the same way we defined sequence back in section 1, and expressing this as the first sequence term plus the second sequence term plus the third sequence term plus forever. So basically expressing the sequence as a series is, we call it an infinite series. Okay. The number a sub n is what we call the nth term. And then, most importantly here is this next part. What we can do is we could look at something that we're going to define to be little s. And little s sub 1 is just adding up the first 1 terms. So that's kind of nothing. But s sub 2 we get by adding up the first 2 terms. S sub 3 we would get by adding up the first 3 terms. So we're creating this variable s, where this variable s is just adding up whatever the index is, number of terms of your series. This would lead us then to s sub n, and s sub n would just be adding up the first n terms. This is a finite sum, so this is going to have a value to it. And we're also going to call it to it, these s sub n's we're going to call the sequence of partial sums. So these s sub n's, these partial sums, create a sequence of the infinite series. I know it's confusing, and I know it's kind of hard to go back and forth between the definitions of sequence and series, but just make sure you don't get them confused. Adding up an infinite number of terms is the series. If I look at all of the partial sums of that series, it creates a sequence. If I take the limit of that sequence as n goes to infinity, that gives me the sum of the infinite series, which is what we did in that last example. Okay, a few more things to write down here. If the sequence of partial sums converges to a limit L, we say the series converges and its sum is L. So that's what I was just saying. If I look at the sequence of partial sums here, and if that sequence of partial sums converges to a limit L, that also means that the infinite series converges, and we say that the sum of the infinite series is L. Likewise, if the sequence of partial sums does not converge, then we say the series diverges. So this happens quite a bit. It's very rare for a series to actually converge to something. More often than not, it diverges. So just as an example, if you had the series 1 plus 2 plus 3 plus 4 plus forever and ever and ever, just the series of the whole numbers, this definitely diverges. It blows up to infinity. Okay, so pausing it here, and we're going to start the next video where we're going to jump into a special case of these series.